On these logistic curves, we don't have tons of problems like this, but we do get a couple. And so we'll see a couple like this in the future. We kind of look back at this one right here. But when you see a logistic curve, typically involves an LN graph, right? And so your LN graph will do something like that. A lot of times it might be doing something like that. And so the thing is, all the logistic curves, though, they're gonna have a point like a ceiling where that graph levels off, okay, where that population levels off a little bit, whether it's an increasing one or decreasing one. And where that levels off, see, when they ever ask us for the what's the limit as t approaches infinity, they're wanting that leveling off point. And see, the leveling off point, that's going to be where that derivative is equal to zero, because the slopes are approaching horizontal, the slopes are approaching zero, so the derivative is going to be equal to zero. Now, I'm about to give you a couple shortcuts for A and B in a second here, but let me just talk about what's going on. I'm not sure why they're giving us two different points here, but when I see the limit as t approaches infinity for both of them, again, you're finding that leveling off point. You want to know where is this first derivative that they give us equal to zero. So you just set that equal to zero, you get p equals 0 and p equals 12, and then always choose that number, not the zero, choose that number. That's going to be what we call like a carrying capacity right there. When you see a limit as t approaches infinity, that's always where that first derivative is equal to zero. Part B is saying, when is the population growing the fastest? Now, population growing, that's like first derivative. Where is that increasing the fastest? They're asking us to maximize that first derivative. Anytime you want to maximize or minimize anything, you got to take its derivative and set that equal to zero. So this involves taking the second derivative and setting that equal to zero. And then if you take a look at, like this, where that second derivative is equal to zero, possible inflection point, right? You see how you got like a positive slope there, and then it gets a little steeper. Then right there is going to be the steepest, and then it gets less steep after that. So that's the point where that slope is going to be the steepest, and that's going to be the maximum slope or the maximum first derivative, the maximum rate that thing is growing there. So that's why we're going to take that second derivative and set it equal to zero. So the long way to find it is to do a product rule right here. So everything is in terms of one variable. You don't need to worry about tagging on a dp dt or anything like that. Just treat it as just like x's and just do your normal derivatives there. So there's my first function times by the derivative of the second, plus the second function times by the derivative of the first. And then you could see my work for that. I mean, it's pretty simple there. I just worked the fractions together, reduced the fractions, cross multiplied, got that p was equal to 6. And that's the value of p where it's that population is growing the fastest. Now, shortcut time. When you see this logistic thing, they typically will ask us two big things from part A and part B. And that's on the multiple choice as well. We'll see a couple practice with that. But if I see a logistic curve or anything that looks like this, and I see limit as t approaches infinity, that's called the carrying capacity. And that's always going to be where that first derivative is equal to zero. So I would kind of pause and jot that down if I were you. But when you see a limit as t approaches infinity, set that first derivative equals zero. That's called the carrying capacity. They might ask you for the carrying capacity. You know that's where that first derivative is equal to zero. Now, anytime they ask you for where is something increasing or decreasing the fastest, that's always going to be the point of inflection, like we talked about. So the long way is taking that second derivative, set it equal to zero, but it's always going to be half of that carrying capacity. Notice above, we got 12 for part A. And then for part B, I can just simply write down, that's my carrying capacity. And then half of my carrying capacity would be 6. And they would accept that for the justification right there. So the rate that's growing the fastest is just half of that maximum number that we already found right there. So that's kind of like something we're kind of learning right now, but a couple quick ways in order to do those problems. So if they say where it's increasing the fastest, half of that maximum point, that's half of that carrying capacity. So it's the 6 instead of the 12 right there. All right, now letter C, I just want you to, like I said, you should be listening to these and then trying all of them on your own, but you know how to do all of letter C. It's just, you just got to make sure you practice and you got to be careful with it. And you didn't have a calculator on this problem. And so these are the ones where we're going to solve a differential equation, right? So I'm going to multiply both sides by the dt and see how I got that y's with the dt. I can't have that. So it doesn't really matter what you do with the 5, but that y has to be moved over here. So I think I just multiply both sides by 5 with a y, got the y's with the dy, got the t's with the dt. And then you integrate both sides. Once you separate your variables, you integrate both sides because it's telling us to find y. So I have to integrate that derivative to get the original function there. And then, so integrated both of those, Remember the plus C, we always put the plus C on the side the X's are on, and then they give us this point to figure out what that C value is. So I plugged the 3 in for the Y, plugged the 0 in for the T, got what my C value was, plug that back in right there. And then what I like to do is if I have LNs on both sides, I like to get all my LNs on the same side. So I move that over there, factor out of 5, divided everything by 5, had the ln, use my pre-calc properties and merge that together, and then you can go e raise all that stuff is equal to y over 3, and you could times everything by 3, and that's what we want for part C right there. So we know how to integrate both sides. We know how to work with the ln's. It's just the solving stuff at the end. We want to make sure if you got ln's, move them all on the same side and be careful with the arithmetic because you had to do that stuff without the calculator there. And then the last part of that, it says for this function we just found, what's the limit as that t approaches infinity? And so if we do the limit as t approaches infinity of that function, if I plug in infinity here, it's a little tricky because you got like infinity on this one and infinity on this one. And that's like infinity minus infinity, which is that weird or indeterminate form stuff there. So I went ahead and got like a single fraction. And then what that gave me is I knew that was going to be like a negative infinity on the top because it was negative t squared. You look at that highest exponent. I guess you could have done that like over here, but that negative infinity. So we get 3e to the negative infinity. And remember the negative exponent, that's like 3 over e to the positive infinity. That's like 3 over infinity, which is equal to 0 there. So if you get it in terms of one fraction like that, then you're looking at the highest degrees. You just have the number on the bottom, so that's not going to affect it all. But then you got this negative like billion squared when we look at those highest degrees right there. So a little tricky at the end there. But we'll see a few more of those in the future. Not a lot of them, but we'll see some of them when we do our multiple choice practice as well.